techniques.
And a lot of us have done probability and statistics. And then we have decision analysis. And then QE models. They fall under probabilistic techniques. Then we have network techniques or network models. And these network models entail network flow models and then project management models. We'll deal with at least project management models. Then we have some other techniques which include analytical hierarchy process, in short AHP. Then we have nonlinear program. See, we have linear program. We also have non-linear program. Then we have simulation models, forecasting models, and then inventory models. If you go to the companion website of the Taylor, which is a textbook that we are using, they have some materials on these other techniques. The simplest method is also a method of resolving linear programming problems. Transportation and assignment models, non-linear programming, game theory, Markov analysis, branch and bound method. All these have materials on the website of the publisher. Now, just a quick rundown of what the models entail. First, linear mathematical programming. These models usually require the statement of a clear objective. And we would recall from last week that an objective can be to maximize profit or to minimize cost. So that you maximize or minimize your objective under restrictions, which we call constraints. And then you have known parameters. You know, there are numerical values. And we saw from last week, we gave an example of number of pounds of the metal that was available for us to use to produce the good that we were supposed to produce. So these linear mathematical programming models are usually deterministic models. So when we say something is deterministic, it means that there is certainty about the solution. And there is no probability attached to the conclusions that we make. Okay? So last week, when we established the break-even point, there was what? Certainty about the break-even point. Okay? Then we have probabilistic techniques. We talk about statistics and probabilities. For them, you are dealing with situations where there is likelihood of something happening. So there's no certainty. Okay? So there's a likelihood. So you attach probability to the occurrence of the event. So we say that the results contain uncertainty. Then we have network techniques. And these network techniques are usually formulated in the form of diagram. And the modeling approach can be deterministic or probabilistic. Okay. Then the other techniques also, you look at them, you can also take either a probabilistic approach or a deterministic approach. But forecasting, simulation, multi-criteria model, analytic hierarchy processes. They all will group them under other techniques that we will not go through. We may just pick either forecasting or simulation to look at. We will not look at the rest of them. Time permitting. Now, linear programming or management science has become very necessary for business schools around the world because of their practical relevance. So, management science, as I mentioned last week, is not a theoretical course because it is just a set of tools that we use to scientifically resolve real-world management problems. So, if you look at real-life situations, management science techniques have been used for project planning, capital budgeting, inventory analysis, production planning, and then scheduling. How to schedule. So if you are an airline, how do you schedule your flights across different countries of the world so that you can maximize profit? Okay. And there are also journals that are publishing practical live applications of management science tools. And Informs is one of the institutes that is publishing practical applications of linear programming models. It is said that when Obama was planning his campaign, somewhere around in 2012 thereabout, what he did was to assemble a crack team of management scientists, computer programmers, to use those management science models to analyze the electoral environment of the United States of America, which can tell him which voters to target, which states to concentrate his campaign on, which age groups he can target and all that, in order to have a successful campaign. So it was little wonder that when Obama hit his campaign run, he drowned his competitors in the campaign process. Such that I'm not sure it will take a long time for such history to repeat itself, where a black man will become the president of the United States of America. Okay. If you look at Burger King, you know that they are into the production of burgers. They use linear programming to determine the best blend cuts of meat that they have to use in preparing the burger so that they can maximize profit. Integer programming was also used by American Airlines in order to determine the optimal flight schedule that can help you to maximize profit. There's a technique that we call the shortest route algorithm. It was used by Sony to develop an onboard car navigation system. Then project scheduling techniques, which we will learn, God willing, was used by a contractor to rebuild the Interstate 10 damage in 1994 earthquake. This is an interstate road. It's the fourth largest interstate road in the U.S. And project scheduling technique was used in order to reconstruct that particular highway. Now, decision analysis, which we are likely to do, was used in Finland for environmental planning. Key models are used by Disney and Disney World so that they can schedule the waiting time line entertainment and give their clients the best satisfaction when it comes to movies, okay? And so on and so forth. So what we will do is to go through the techniques so that you can understand how they are applied in real life, and then also the objective is for you also to possibly use it to resolve problems at your workplace. And that brings us to how management science models support decision support systems. In other words, how are management science models integrated into decision support systems. Now, when we talk about a decision support system, we are basically referring to a computer-based information system. And having done business information system, I think that you should know decision support system, because I'm sure that you came across ERP, Oracle, OLAP, among others. These are decision support systems. And their key features are that one, they are interactive. Number two, they are connected to databases. And they have management science techniques embedded in them. Number three, they can address what-if analysis or what-if questions. What-if analysis is also one of the techniques that we can use in management science. What if this happens? What will happen? Then we have, they can perform sensitivity analysis, the decision support systems. And then also, they are used over the internet. At some other places that I had engagement with, they were using ERP. Okay. So with ERP, you can connect all aspects of what the organization, marketing, finance, HR, all activities can be interconnected. And what one person does at his desk will reflect in the desk of the other person, so that there will be a complete flow of work activities. Now, this is how management science is integrated with decision support systems. So you have a user interface, the decision maker is here, then there's a database connected to the interface. Then you have the internet, which is running the entire system. But embedded in the interface are management science models, which would be linear programming models, probabilistic techniques, or network models. But the problem is that not many organizations are maximizing the use of the management science models that are embedded in decision support systems. And that's what we have to change through our understanding from this course. So there are some questions that you can try your hands on, which are based on what we did last week. Last week we did break even analysis, okay? And I even asked you to try. I hope you install the QS. The KM. You see? Why?
Yes. Okay, you can search and download it. Some of them, what it's it's like it's a low version. So you can search for a higher version, which is the same you want to pay.
It's free.
It's free. I've not downloaded. I've downloaded. No, we downloaded. In our lecture, we downloaded.
Please. Either you use the one I sent you or download it. Because next week we will need it. Next week we will need it. Today we will do the algebraic calculations and the graphic. But next week you will have to come here and demonstrate to me that you can use XLQM. All right. Because as we shall come to know, the linear programming models, where you have more than two decision variables, it is difficult to calculate algebraically. Okay? So if I give you one question to go and calculate algebraically and it is having 5 decision variables, it will take you forever. Okay? But if you have to do it over a computer, it will take less than 4 minutes. Okay? So it is good that next week when you are coming, or today we may not use the computer to resolve the problem. These are very basic problems. The ones we are going to resolve today, they are very basic. Okay, even somebody in GHS with simple knowledge of simultaneous equations,
with simple knowledge of
to be able to resolve it. So that one we don't need computer.
We don't need
to do that. But for next week,
to do that. But for next week,
you need computer. You have to install the XLQM so that when I click, you also click. Okay. I don't want to click and you'll be sitting down. And then one more thing. You see, I've seen that a number of you, when you come to class, you are not paying attention. Okay? You are not paying attention. If you are not paying attention, this course will not be easy. Okay? Because as for me, I only need to give you the calculation question and I go and sit down. That's all. Okay? So no matter what, you have to force yourself to understand it. That's the only way out. Okay? So you have to put yourself in the course. You have to put yourself in the course so that things will be easier for you and for me. Okay? All right. So now let's we'll go to our first major topic. Which I said is quite basic. So today we are going to look at linear programming, a graphical solution. Now, there are several ways of solving linear programming problems, but some of the easiest is using graph. But the main issue is that the normal graph that we know has basically 2 dimensions. You have your what? X-axis and your what? Your Y-axis. Which means that typically you can plot only 3 variables. Okay? But it is possible to make it 3-dimensional by introducing another axis so that you can plot a 3D graph. But when you have more than 3 variables, it is impossible to use the graphical approach. So the graphical approach, we usually limit it to 2 variables, where we have 2 variables. Okay? And that's what we are going to do today. So this is what we'll look at, how to formulate the model. Then we'll have an example of a linear programming problem, which is a maximization problem. Remember that we said in linear programming, you must have an objective function. And the objective function can be a minimization function or what? A maximization function. So today, we would stop at the maximization model as an example. Next week, we will do the minimization problem. Okay. So we'll deal with model formulation, a maximization model example, and then graphical solution of the maximization model example. Then next week, we will quickly look at the minimization model example, and then we go into computer solution of linear programming models. All right. So we are saying that for business, every day involves making decisions. And most of those decisions may involve 2 things, one of 2 things. Either you are minimizing something or you are maximizing something. So that becomes the objective of the firm. So what linear programming modeling does is that it simply uses linear algebraic relationships to basically represent a firm's decision under the environment of a business objectives, but subject to some resource limitations. So it's basically a linear. When we say, maybe let's start with the basic. When we say a function is linear, what does it mean? Okay. Back to math class. Linear, a function is linear. What does it mean? Yeah. Say what? No. The emphasis is on the linear. Linear. Now, you know that variables, if you take x, you can have what? X raised to the power 1. So when you just see the variable as x, what it means is that x is raised to the power what? 1. When x is raised to the power 2, it is no longer linear. Okay? So it means that all the variables we are going to deal with, they most often will be raised to the power 1. And that makes them linear. Okay? And you can plot them. When you plot them, they will lie on what? A straight line. All the values on the point will lie on a straight line. That's why we call them what? Linear. So you will not see x squared in our analysis, okay, or x cubed. Then we are moving into nonlinear programming. Remember, I mentioned what? Nonlinear programming. So when you now have x squared, x raised to the power 3 or 4, or 5, then you are now dealing with nonlinear programming. But what we are going to deal with largely will be linear programming. Linear programming. Okay. So you have an objective, you have resource constraints, and then you have decision variables. Okay. So what are the steps in linear programming? First, you have to identify a problem as solvable by linear programming. Not all problems are solvable by linear programming. Okay. So you first have to make the decision whether the problem you are encountered with is a linear programming problem or is a problem that is solvable using linear programming. Okay. Then once the answer is yes, you now formulate a mathematical model of the unstructured problem. The problem itself is not structured. It's just either a table or a sentence or two that describe the situation. So you now turn it into a mathematical model. After turning it into the mathematical model, you now solve the model. Okay. So that once the solution is provided, you can now make a decision. Yeah. So last week we mentioned these, but just to recap them. The model has the following components. First is what we call decision variables. Decision variables. And these are just your x's, your y's, and your z's. They are the activity variables. In other words, if it is a firm that is producing yarn, then the units, the number of tubers of yarn to produce is the decision variable. If it is producing maize, the number of bags of maize to produce will become what? The decision variable. Then there is an objective function, which can be what? A minimization function or what? A maximization function. Then there are constraints. Resources are not in abundant supply to the firm. So when the firm is maximizing or minimizing, it faces some constraints. So for instance, the maize farmer does not have the whole world to himself as his farmland. He probably has 5 acres. So much as he wants to maximize profit, he cannot grow more than what? 5 acres. So one of the constraints that he may face is what? Land. So he will be maximizing his profit subject to what? He using 5 acres of land at the most. Okay. Then there are parameters. The parameters are simply the values that are attached to the variables in the model. So for instance, you can say that you will need what? 2 hours of what? Labor in order to produce 1 unit of the product. The 2 hours becomes what? A parameter. The 2 becomes what? A parameter. So the parameters are the values that are known, which you will then use to what? Resolve the values that are not known. Okay. So for a typical linear programming model, you will have decision variables, objective function, constraints, and then what? Parameters. Okay. So as an example of model formulation, we said that the first step is that you define the decision variables. So for instance, it could be how many bowls and marks to produce for a firm that produces bowls and marks using clay. Okay. Then define the objective function. And the objective for this firm is what? Maximize profit. Then you define the constraints. The constraints are that there are resources available, and these resources are what? Clay and labor. But the firm has limits as to the quantity of clay and then the labor that it can command. Okay. Okay, so let's now look at any question before we look at a maximization model. Simple maximization model for this illustrative example. Okay, so let's take note of this maximization problem. Very simple problem. So this Beaver Creek Pottery Company. Okay, so that's the name of the company, which is in the business of producing bowls and marks. It has realized that in producing bowls and marks, it will need labor. And 1 hour of labor supply will produce 1 bowl. Okay. But 2 hours of labor will produce 1 mark. Okay, take note of that. 1 hour of labor will produce 1 bowl. However, 2 hours of labor will produce 1 mark. Okay. Then, for clay, to produce 1 bowl, it needs 4 pounds of clay. So 4 pounds of clay will produce 1 unit of what? The bowl, or 1 bowl. Then 3 pounds of clay will produce 1 what? Mark. In terms of profit, it knows that when it produces 1 unit, that is 1 bowl, it will make $40. If it is able to produce 1 mark, it will make $50. So this is the unstructured problem, okay, that the firm is facing. Okay. And this linear programming problem is called the product mix problem, because the 2 products can be made using the same set of resources. So there are competing resources. You have clay, you have labor, and you can either use the clay to make only bowls or to make what? Only mats, or what? A combination. Okay? But you want the combination of the 2 to make. That will help you to maximize profit. Okay? And that is what this problem is about. So the question that Beaver Creek is asking, how many bowls and mats should be produced in order to maximize profits, given labor and materials constraints? Then you have product resource requirements and unit profit. Okay. So now, these are the resources available. They are the ones that will define the constraints. Okay. It has a maximum of 40 hours of labor per day. 40 hours, that's the maximum. Then the total amount of clay usable is 120 pounds. So clay is limited, labor is what? Limited. And you want to produce bowls and what? Clay. Bowls and mats, thank you. Now, the decision variables. Number 1, we can label it X1, which is the number of bowls to produce in a day. That's the decision variable that is confronting this firm. Another decision variable is the number of mats to produce a day. So that is the problem that is facing this firm. How many mats to make a day? How many bowls to what? Make in a day? Subject to having a maximum of 40 hours of labor and then 120 what? Pounds of clay. Okay. So you realize that if you go back to the question or the table, you would find that the profits are given. Okay. So it is critical for you to have in mind what the firm should be about. Remember that this particular firm wants to what? Maximize what? Profit. And maximum profit will be what? A sum of what? The profit of what? The 2 commodities. Not so. The profit you make from what? Bowls, and the profit you make from what? Marks. we are told that if it makes one bowl, it will make what? $40 as profit. Okay, so we say that we are maximizing profit, which is Z. We usually, as for those nomenclatures, remove this one. As for those nomenclatures, we are not too strict with them. You can say maximize R or maximize Q. Economics, we usually like maximize pi, which is profit. Okay. Now, so that the sum of the profit from the two commodities will give is what you are maximizing. Okay. So you start first by stating the objective function. Okay. So that the objective function is what? Maximize. Z. Maximize profit. So Z is standing for profit. Take note. Which is equal to, we said what? If you sell one bowl, you will make what? 40. So 40 of X1, and then the mark if you sell one, you get what? So $50. So, but you don't know, this is what you are looking for, the X1 and the what? X2. So you want the right amounts of what? X1 and X2 that you will produce in order that this profit Z will be the highest possible, given the resources available to the firm. Okay. So that once we identify the objective function, we can now state our resource constraints, because we are told that we do not have all the wealth to ourselves. We have only 40 hours of labor available. And if you go back to the table, we said that 1 unit of what? 1 hour of labor will get us what? So, but 2 hours will get us what? 1 mark. Okay, so we know that we have what? So we are now dealing with our constraints. Such that we said 1 hour will give us 1 bowl. Okay, so I could have written the 1, X standing alone means what? Is multiplied by 1. That's why I have not put it there. Okay. Plus, we said we need what? 2 hours to make 1 mark. So 2 hours times what? X2. But we do not have, we have a resource constraint. The maximum hours that we can afford is what? 40 hours. So we cannot exceed 40. Okay. So less than or what? Equal to what? 40. So this is our constraint 1. And this is the labor constraint. Okay, so this is the labor constraint. But labor is not the only constraint we are facing. We are also constrained when it comes to what? Clay. Okay, we have only 120 pounds of clay. And going back to the table, you will see that 4 pounds will produce what? Is required for one bowl also. So 4x1 plus 3 pounds will be required to produce what? 1 mark. So 3x2. And we cannot use more than 120 pounds. So either less or exactly equal to what? 120. And this is what? The clay constraint. Any problem up to here? Sophia, any problem? You are with me? Yes. Madam, are you here? Are you here? We are together. Okay. Yes, please. Please speak up. Yes, it's not, it's on the other page. It's not on this table. Yes, it's provided. Yeah. It's provided. Now, yes, please. Good point. But the question is, where are the numerical values to prove that? In other words, if you concentrate on S1 alone, what will be the maximum profit? Compared to if he concentrates on X2 alone, what will be the maximum profit? Compared to if he decides to combine. You get the problem. So our job is now to show that what you are saying will not hold. And that's what we are doing. Okay? When we sketch the graph, you see it. Okay? What we are talking about is one of the possible solutions. So we call it a feasible solution. But it may not be the optimal solution. Okay. Now, X1 and X2 are the decision variables. If X1 is negative, we can produce. If X2 is negative, we can produce. But X1 can be 0. X2 can also be 0, but not at the same time. Okay? So we add a third constraint, which we call the non-negativity constraint. Because if both of them are negative, you can't produce. So we now say that X1 is greater than or equal to 0. And X2 is what? Greater than or equal to 0. In other words, the firm has some resources. That's what we are assuming. The firm has some resources. If a firm doesn't have resources, it shouldn't bother us with linear programming problems. Yes. Yes, yes. But there are yes. We call that the non-negativity constraint, which says that the firm must at least have some resources to work with. Okay? Or the firm must at least produce something. The firm must at least produce something. So I would say that this is the most difficult part where we have done. And I'm happy that you have all said that you are following. Yes. You say, if you use this, you'll be complicating your problem. You have to convert back. You understand that? It's better to work it in the units that the question has provided. Yeah. Coordinator, you want to help us to solve our linear programming problem. Any information? Oh. Okay, okay.
Hello. I hope we are doing well. Praise the Lord. That with me, or against me. It is well, okay?
Yes, somebody was there a question? I've answered your question. Okay. So I said that I'm happy that up to this point, all of you are saying that you are following what is happening. And I'm a happy person. Yes. Which one? Yes. So I'm saying that one arises as a result of the fact that we are saying that the firm must at least produce something. That's how we arrive at it. If the firm is not producing something, then there's nothing to maximize. Okay, we cannot maximize for a firm that produces nothing. Okay, so we are saying that at least the firm must produce something. Okay. So you can look at it more or less like an assumption, because when it comes to resolving the problem, we may not, you see that we will not use it. Okay? But it makes the problem complete. Okay? Now, when you have set up the model like this, yes, please. The 120 is part of the information given in the question. It's part of the information given in the problem. The 120 is the maximum amount of clay available to the firm. Okay, just as 140 is the maximum labor hours per day. Okay. Ask all the questions. So Okay. Now, when you reach this stage, you have several solutions in the universe available to you. One of them, you can use graph. You can also use algebraic approach. Okay. For most of you, what will seem to be the problem is this symbol. How to navigate that. But that is simplified by approximating it into an equality constraint. In other words, you remove the less than and make it what? Equal to. Then you can solve it mathematically. Okay. So what we'll do is that, so this is the formal statement of the model. So this is what we call the mathematical statement of the model, which is what we have enumerated. So you write maximize profit subject to, don't forget, subject to. So maximize profit subject to labor and clay work constraints, keeping in mind the non-negativity constraint. Now, we have a term we call a feasible solution, and I alluded to that when he asked me a question. A feasible solution is a solution that does not violate any of the constraints. In other words, a feasible solution will be values of x, x1 and x2, that will plug into this constraint function. And then the left-hand side will not be more than the right-hand side for any of the constraints. So we call it a feasible solution. So for instance, if we assume that x1 is 5, and then x2 is 10, so we put 5 here and then 10 there, we are going to have the left-hand side being what? 25. Yes, which is less than 40. We are moving to the solution. Exercise patience. Don't worry, we'll get there. We'll get there. Yes. Yes. You can use Q. You can use R. That one, there's no problem. Because these are just symbols. Okay, so the X's, the Y's, the Z's. Why? But you will see that most textbooks, they like you say X and Y. Okay, X and Y. So if we plug 5 for X1 and 10 for X2, our total labor will be 25 hours, which is less than 40 for the first constraint. If we also do same for the second constraint, we'll get 70, which is less than 120. and they do not violate any of the constraints. So we say that they are what? Feasible solutions. Yes. Yes. And I said yes. Yes, you are trying to make things complex for yourself. Okay. You can do that. That's fine. Yes. Yes. It's standard.
Yeah.
So take note, feasible solution. We have infeasible solution. And it violates at least one constraint. If you have a solution that violates one of the constraints, then it's infeasible. In other words, the firm cannot use that, can't achieve it. Okay? So, for instance, you have 10 bulls and then 20 marks. If you slot it in the first equation, it gives you 50 hours, but we have only 40 hours. So we say that that solution. So if you were solving this problem and your answer is there 10 bulls and then 20 marks, then the solution is wrong. It's infeasible. Okay, so take note of that. As I told you, when you have two decision variables, you can use the graphical approach to resolve it. But where you now have more than 3, because 3 you can do it, but it won't be easy. Okay. But where you have more than 3, it is better not, you cannot even use the graphical approach. Okay. So, but at least we can try to see how we can employ the graphical approach to resolve the linear programming model. That nice. Yes. What I would say that among the feasible solutions is an optimum solution. Yes. So, and that's what we are looking for. And after plotting the graph, we'll show you the feasible area. There's an area that is the feasible area. All the region under that area, they are feasible. The firm can achieve them. But as to whether they are maximum or not is the question. So you have your axis. X1, and then what? X2. Remember that because of the non-negativity constraint, we cannot come here, the negative region. Okay? So that's part of the reasons. We cannot go to the negative part of a graph. Okay? So I label the graph. Now, it's disconnected. No. Yes, I've seen it. Which one? In 20 should have been 50. No, it's not up. Now, when you have the graph and you lay out the dimensions, we have to plot these constraints over here to be able to solve the problem. In our canal. So they are on. Okay. So what we need to do is to plot the constraints over here. And how do we do the plotting? You plot them. So for instance, if we want to plot this, what you do is that first, you look for values for x1 when x2 is equal to 0. And values for x2 when x1 is equal to what? 0 for this. So let's start with, first, do you understand what I said? I said to be able to plot the constraint, assume one of them to be equal to 0 and solve for the other. Okay. So first, let's take the labor constraint and assume that x1 is equal to what? 0. So if x1 is 0, it will mean that what? This place will be what? 0. Okay, so 0. So let me write it down. If x1 is 0, it implies that 0 plus what? Is equal to what? So that it implies what? Is equal to what? 20. So it means that here we are plotting the coordinates what? X1 is what? 0, and then x2 is what? So x1, 0, x2 is what? So here, that's the point. Okay. So we now come to what? If x2 is equal to what? 0, it will imply that x1 will be equal to what? Not so. Because this is what? 0, not so. For x2 is 0. Okay. So here we are saying that we are now solving the first equation. If x2 is equal to 0, if x2 is 0, this whole term what? Is 0. And x1 will be equal to what? 40. X1. So this is just one x1. So maybe let me just delete the 1. You now see that this is 0 by assumption. So x1 will be equal to what? 40. So the coordinates here will be what? 40 what? 0. So when what? X1 is what? Is what? 40. And x2 is what? 0. So that is what? This point. So we simply join the 2 points. So this is the labor constraint. I don't want the board to be messy. Otherwise, I would have labeled it labor constraint. Okay, but that's the labor constraint. But we also have a clay constraint. Okay. We also have a clay constraint. So we now have to come here and repeat the same process. So let's assume that x1 is equal to what? 0 for the second constraint. Then it will mean that this will be 0, not so. So it will imply 0 plus what? 3x2 is equal to what? 120, which implies that x2 is equal to what? 120 divided by 3, which is what? 40. Hello. Okay. 40. So the coordinates are 0 and what? My friend, you have come late, and you are disturbing us. So the coordinates are what? X1, 0, X2, what? 40. X1, 0, X2, what? 40. So we are here. First rep. Are we together? Yes. So we are now left with what? X1. The coordinates if X2 is 0. So if X2 is equal to 0, it will imply what? That's from here. 4x what? 1 plus what? 0 is equal to what? 120, which will imply 4x1 is equal to what? 120, which implies x1 is equal to what? 30. 30. So the coordinates we are dealing with are what? 30 what? 0. So x1 is 30, while what? X2 is 0. X1 is 30. So we are here. So we join the 2 points. Straight line. Okay. All right. So look at the graph very carefully. You will see that there is a region that is common to both constraints. And I will highlight that. That region is called the feasible region. That is the feasible region. Any other area outside the shaded region is infeasible. So any point outside that region is outside the solution to our problem. So if we have point B here, call this point B, this is infeasible. Here, infeasible. Here, infeasible. Here, infeasible. But if you have a point R in the region, it is feasible. R is feasible. Now, when we get to this, we can now get the values of x. If remember that this is just a sketch, so we cannot get it precise. But if you have a graph, to be very precise, okay, so we are approximating. If you have a graph and you establish this, the question is, which solution is the optimal solution? Okay. Mathematically, you can guess. Okay. But let me give you the parameters for deciding the feasible solution. One of the ways of doing that is to assume a value for the profit and see whether how the profit line will lie. So suppose that the profit is, for instance, 800. Oh, it's like the internet is. Let me connect the phone. Yes, you can ask, please.
You make the quality sign that's in the constitution.
No. Yes, you use the equality sign, not the inequality sign. The equality sign, yes. You find that when we are resolving the constraint, I use what? Equal to. Okay. So that we can, the equal to helps you to establish the points. Okay. So at this point, just for us to see the illustration well, I'm going to wipe it and leave only the feasible solution. Connecting. No, I can't connect anything. But I'm connecting our guys here. Now, what we can do before I just help us to resolve the issue is that first, let's assume a value for profit. Let's assume that profit is $800. In other words, when we sum the Z is 800. So 40. So this is just to help us to understand how the solution is arrived at. It doesn't mean that when you have a problem, you have to make this assumption for the profit. Just to, I could just point to you what the, the solution is, but I have to let you get the intuition. So let's try to see how we can plot the function, the profit function. Okay, this is 800 for the profit. So that one, we use the same approach to get the coordinates for x1 and x2 so that we can plot it. So let's assume that x1 is equal to 0. then it will mean that what? Or have what? So that x2 will be equal to what? 800 divided by 50 will be what? 16. So the coordinates here will be what? 0 what? 16. So 0 for x1, and then what? 16 for what? X2. So let's say that is somewhere here. So if x2 is equal to 0, then 800 will be equal to what? 40 what? X1 plus 0, which means that what? X1 will be equal to what? 20. Okay. So the coordinates here will be what? 20 what? 0. So 20 for x1, x2 is what? 0. So 0, 20 here. So we connect them with a straight line. So this is our profit function or maximization function. Now, it means that the profit that we gave as an assumption is too small. There's still a gap. Okay, it's too small. We can continue to make we can continue to make assumptions, but we don't have to. If we get a larger profit margin, it will take us outside. Now, suppose that we are taking this profit line the way it is, shifting it outside the feasible region, which will be the last point that it will touch. And let me label the points. A. So this is a point A, point B, point C. The way it is lying, if we are taking it out of the feasible region, which of these points will it touch last? Is it A, B, or C? Look at the nature of it. If it's going out, it will be like this. So it will be B. Now, one of the characteristics of linear programming is that the solution is always a corner solution. This is a corner. We have corners A, B, C. So we call them corner solutions. They are corners. So it will not be the straight line part. So they are out. So the solution must be one of A, B, C. And the one that is farthest from the origin will be the optimal point. And that will be the solution. Okay? If you want, you can slot in the values. And that brings us to your question. So for instance, this solution, to get the maximum profit, you have to set x1 at 0, and then what? X2 at what? 20. The profit you will get is this area. This one, you set x2 at 0 and x1 at 30. The profit you will get, that is what is here. This one, point B, we have to trace it down straight. And that, if your graph is accurate, this will be 24. Okay? So it means that x1 is 24 from the graph. This one, the same. You trace it to the x2 axis, and then it is somewhere around what? 8. So it means that our graphical solution is that what? X1 is equal to 24, sorry, 24. X2 is equal to what? 8. So you now plug these values into the objective function. To get the maximum profits. Remember that we said Z is equal to 40x1 plus what? 50x2. So we have Z is equal to 40 what? 24 plus what? 58. Back to your calculators. So everything. This is what? 60 or 16? Plus 400, and that gives us what? So that is the maximum profit this firm can make, given 40 hours of labor available, and then also what, 120 what, pounds of clay. That's the maximum profit it can make a day. Okay. Now, this is the graphical solution. Okay. But because of sometimes you may not have a precise graph. I see that you are using an exercise book. It's not a graph sheet. So there will be some inaccuracies if you don't use a real graph. Okay. So what you can do if you are not using a graph is to solve it algebraically, which is rather easier. Okay? You solve the problem algebraically. And that is simply solving the constraints. So constraint 1 says what? X1 plus what? 2x2 is equal to, and then constraint 2 says what? Is it 4 or 3? Plus 3x2 is equal to what? 120. So call this equation 1. Call this equation 2. Okay? So to solve this algebraically, you can make x1 the subject in this equation. That's the first equation. Okay? Make x1 the subject in equation 1. So that will mean that what? X1 will be equal to what? 40 minus what? So knowing that this is what x1 is, we come and put it in equation 2. Don't go and put it back in equation 1. Okay? If you go and put it back to equation 1, you'll get 40. Okay? So you don't go and put it back there. So you come to the second equation, and then wherever you see S1, you insert this. Okay, so we have 40 minus what? Close the bracket. Don't forget about this. That's a temptation. Yes, I'm coming. 3x2 is equal to what? 120, yes. I don't understand what you are saying. You don't need to do that. You don't need, there's no further work to do there. Yes. Yes. For simultaneous equations, there are several methods. Okay. There are several methods. So you use the one that is easier for you. Okay. So we have what? Sorry. Then minus what? Plus so you see that you have like terms. Okay, so we can group them. So we can bring the 120 here and then take the x's to the other side. Okay. One 20 is equal to what? 8x2 minus what? Okay, so we have what? It's equal to what? So from here, x2 is what? Which implies x2 is equal to 8, which is what we discovered from here, the graph. So it helps you to establish the precision of the graph work. So once we know x2, we know x1, because that one is easy. We take any of the equations and we put what? X2 there, and then x1. So if we insert the value in what? Equation 1, we have what? X1 plus what? 2 what? Is equal to what? So that x1 is equal to what? 40 minus what? Which is what? 24. So these are our solutions. Okay. So you see that the algebraic solution is even easier than the graphical solution. Okay. It's even easier. Any question before we bring the class to a close? Yes. I'm here to determine that.
The software program.
Yes.
Where we have a decent and solutions. Providers will be guys, I don't know whether they were actual solution for them. So that's what they will demonstrate.
There are no solutions. This is the solution. This is the solution. Okay. All right, course rep. Yes, please. And I'll let you have it. I updated it. Okay. Even this one, I updated it. So I'll send you the updated one. Okay. All right, so see you next week. All right.
Which one is that? For those who join us, may I know their course name?